This episode is sponsored by DataCamp. You can start building your data science and analytics skills by clicking the link in the description. One of the hardest places to explore in space is actually the closest part. It's a region known as near space, high in Earth's atmosphere. The main problem is that there's just enough air to mess up a satellite, but not enough for regular aircraft to fly. Because of that, we know so little about this part of space that it's been nicknamed the ignorosphere. Luckily, scientists are creative. To probe the mysterious near-space region, they've come up with all kinds of clever tricks, from bouncing radar off of meteors to levitation by light. And it's helping us get a better idea of what near space is really like. The so-called ignorosphere is properly known as the mesosphere and lower thermosphere, or MLT. Because sometimes the term near space just isn't fancy enough. But whatever you want to call it, it stretches between about 60 and 110 kilometers above Earth's surface. And scientists have learned just enough about it to know it's fascinating and an important place to study. It's home to a bunch of bizarre phenomena, like wispy clouds that shine at night and an orangey color that surrounds the planet. It's also the link between Earth weather and space weather. So we need to understand the MLT to be able to model the energy entering and leaving the planet, which is especially important as we try to understand the future of climate change. So researchers have looked into a bunch of different ways to study what's going on up there, and it is possible. One way is with sounding rockets. These tiny rockets spend just a few minutes in the atmosphere or in space. They carry a few instruments up to quickly collect some data, then come back down without ever entering orbit. Sounding rockets have carried out lots of experiments in the MLT, measuring things like the amount of dust and ice up there. The fact that there are ice crystals in near space at all is actually pretty surprising, considering that the thin air is 100 million times drier than the Sahara. By scoping out particles in the MLT, sounding rockets can help us understand how stuff like ice and dust interacts chemically and how it's affected by radiation from the sun. The hope is that understanding those reactions will help us learn more about those strange phenomena we see in the MLT. But the downside of using sounding rockets is that they can only sample one spot at one point in time. They're not so good at giving us the big picture. And that's a problem, because one thing scientists especially want to model is the MLT's wind field, the way different winds move throughout the region. In particular, the MLT's wind field would tell us a lot about how energy and heat move between Earth and space, which is one of the big mysteries about this region. So to get at that question, scientists turn to a technique called meteor radar. As meteoroids enter the edges of Earth's atmosphere and begin to burn up, the heat they create ionizes or strips electrons from the surrounding air. And these electrons can reflect radar. By measuring how long it takes for the radar signal to get to a meteor trail and back, you can calculate how far away it is. So by bouncing radar off these trails at different points in time, scientists can begin to see how they're moving, which shows how the winds are blowing in the MLT. With enough measurements, they can even piece together a wind field across dozens of kilometers. So sounding rockets and meteor radar are incredibly useful, but there's still a lot we could learn if we could just float something up to the MLT and take some extended measurements. And that's why a research group at the University of Pennsylvania has been working on a completely different way to explore the MLT, using levitation by light, also known as photophoresis. It's a concept that's been around since the 1800s, and the basic idea is this. Imagine you have a small piece of material that's being lit from one side. Think something like a tiny piece of soot. If the material is any good at absorbing light, the side facing the light will be warmer than the surrounding particles, meaning it'll have more energy. So when it gets hit by a cooler, less energetic air particle, it'll recoil, transferring some of its energy to that cooler air particle in the process. The key is that air doesn't bounce off the hot side and the cold side at the same speed. Since the hot side has more energy, the air particles will absorb more energy from it, and that energy translates to more speed in both the air particles bounce and the material's recoil. There are other factors involved that can complicate the physics here, but after lots of collisions, the difference in recoil speeds on each side means that the tiny piece of material starts to move in the direction of its colder side. That's the idea anyway. It's been tested with things like soot, so we know it does work, at least to an extent. It gets even more complex when you're dealing with something big enough to be at all practical, but the team at UPenn found a way to extend the principle to a thin piece of plastic film. They zeroed in on the fact that in photophoresis, the two sides of the piece of material interact differently with the air around them. So they designed a super thin film with a smooth top and rough underside. Their thinking was that just like the hot side of the bit of soot, the rough underside of the film would recoil more from colliding air molecules than the top did, in which case the film would move toward the smooth side, so upward. To test the concept, they placed the film in a low-pressure chamber over a ring of LED lights. As expected, the film drifted upward, floating thanks to light alone. In theory, this should work with sunlight in the low-pressure mesosphere, though it hasn't been tested yet. The challenge is that this is a really weak force. It doesn't take much to counteract gravity on a super light film, so it won't be powering planes or large spacecraft anytime soon. But in the MLT, a little microflyer equipped with a few sensors could go a long way. We're not there yet, but by combining old and new tricks for probing the ignorosphere, scientists are slowly making this little explored region more and more knowable. And to make the world knowable, scientists need to learn how to analyze and understand their data. And in today's world, so do lots of people. DataCamp can help you learn the data science and analytics skills you need to succeed in the real world. Their courses cover everything from statistics to programming. They even have a course on R, a programming language commonly used by scientists to handle big data sets. Lessons on DataCamp are bite-sized and can fit your schedule, and their mobile version allows you to learn from anywhere. If you click the link in the description, you can check out the first chapters of each course for free. So check it out and let us know what you think.